let's discuss the problem at hand. So the question says, determine the maximum volume of an open-top cone with a surface area of 2 meters squared. So let's try a diagram of what this kind of looks like. So an open-top cone is just as shown, and it's basically got three variables. We have the height, the radius, and the slanted height. So it's labeled here, r is equal to the radius, h is equal to the height, and l is equal to the slant height. And this is what the cone looks like. And we know that the equation for surface area is equal to pi r squared plus pi rl, which is the slant height. And here we know that pi r squared is in relation to the base, or in this case the top, and the lateral surface is pi rl. However, the question states that this cone is an open top, so basically this first section of the equation, pi r squared, is not needed. And the new surface area equation for this specific cone in this problem is pi rl. Now, speaking of L, looking back at the diagram, we can see that the intersection point between the radius and the height creates a right angle, and what this means is that L can be described using Pythagorean's theorem. So L squared equals r squared plus h squared, and therefore L equals the square root of r squared plus h squared. So, putting this back in and summing it into our equation, we get that the surface area of this cone is equal to pi r times the square root of r squared plus h squared. So this is what we're given. 2 is equal to pi r times the square root of r squared plus h squared, and what we're optimizing is the volume, which is pi r squared times h over 3, and that is the volume of the cone. Okay, so we've got the equation here. 2 equals pi r times the square root of r squared plus h squared, and we're trying to isolate h here because there's two r's and it's just easier to do so. So we're going to work with this pi r here, try to just isolate the square. So we're going to go ahead and do 2 over pi r equals square root of r squared plus h squared. And now we need to get rid of the square here. So we're going to square the top and the bottom of the function here. So we're going to end up with 4 over pi squared r squared is equal to r squared plus h squared. Now we're going to work with this r squared over here. So we're going to subtract it from the other side. So we get 4 over pi squared r squared minus r squared is equal to h squared. Now it becomes obvious that the next step is going to be taking the square root of this side. However, before we do that, we're going to want to make this into a common denominator. So we can imagine this as r squared over 1. And we can do some cross multiplication now. So over here, let's start doing the cross multiplication. So I've just rewritten the equation here, and let's now cross multiply. So in the numerator, we're just gonna get 4 minus, and it's gonna be r squared times pi squared r squared, and what that's gonna give us is pi squared r to the 4. Gonna be all over that common denominator that we've been trying to get, which is pi squared r squared. And now that is equal to h squared. So what we can now do is we can start to take the square root. So taking the square root of a fraction is the same thing as taking the square root of the top as well as the bottom. So let's go ahead and do that now. So it's going to be the square root of 4 minus pi squared r to the 4 over pi squared r squared. Square root of that is equal to h. And moving on with the next step, the numerator with the square root cannot simplify because of the 4, so that stays. So it's going to remain 4 minus pi squared r to the 4. However, the denominator, the square root, and these squares will cancel out, so we're just going to be left with pi r. So now we've successfully isolated h. This is our equation for h. 4 minus pi squared r to the 4 over pi r is equal to h. Now we can start to plug this back in to our volume equation. So let's go ahead and do that. And going back to the volume equation, we know that the volume is equal to 1 over 3 times pi r squared times h. And so this h is now going to be subbed in here. So it's going to be v equals 1 over 3 pi r squared times the square root 4 minus pi squared r to 4 over pi r. Alright, now we're just going to take this left side here and move it into the fraction. So this is really just pi r squared over 3. So we can just do pi r squared times this, and then 3 times the denominator. We're going to have pi r squared times square root of 4 minus pi squared over 4 over 3 pi r. And now what we see here is we can cancel out the pi and the r's, and there will be an r remaining at the top. So finally, we can describe our volume equation as r times 4 minus pi squared r to the 4 over 3. So that's going to be our final volume equation. And if you didn't see how we did that, this pi and this pi cancel out, and this r cancel out, leaving just 1 here at the top. So that just becomes r, this remains, and these both cancel out on the bottom. So we're left with v equals r times the square root of 4 minus pi squared r4 over 3. And now we can start to take the derivative. So what I'm going to start off with is I'm going to take the 1 over 3. So it's being divided by 3 and 1 at the top. So I'm just going to go ahead and take that out. And what I'm allowed to do is utilize the rule. This is what we end up with. And the reason being that if you're trying to find the derivative of something multiplied by something and the derivative within it, which is essentially what we're trying to do here, 1 over 3 times this, that is just equal to a times f prime. So we can just take the prime of the second part and leave the constant out. So essentially we don't have to do the product rule here in the start. We can just leave the constant out and just take the derivative of this. So that's what we're going to go ahead and do. So utilizing the rule, we can rewrite the derivative of volume to just be 1 over 3 times the derivative of this part over here, so r times 4 minus pi squared r to the 4, and we can rewrite it as such. Okay, so we know we have to take the derivative of this section over here. So taking the derivative of this, we're going to need to utilize the product rule. So we're going to go ahead and do that for the next step. Okay, so let's continue along. So the derivative of the volume is equal to 1 over 3 times. And now the product rule, we're going to take the derivative of r first, so dx r, times just the second component here, which is the square root of 4 minus pi squared r to the 4. And then we're going to add the derivative of the second portion here, which is 4 minus pi squared r to the 4, and multiply that by r. And that is going to be our derivative. And now we're going to need to continue along and work with each section. So let's go ahead and do that. So I'm just going to go ahead and rewrite the derivative just for a little bit more space here. So 803 times the derivative of r times the second is 4 minus pi squared r to the 4 plus the derivative of the second component, 4 minus pi squared r to the 4. So the square root times r. Alright, so let's continue to work along with the derivative here. So we've got v prime is equal to 1 over 3 times, so the derivative of r is just 1, and 1 multiplied by this is just going to be the second component, so we're just going to go and write 4 minus pi squared r to the 4. So for here, we're going to be utilizing the chain rule, and that is because this square root over here is essentially, it's a power of 1/2. So when we bring that down, we're going to be utilizing the chain rule. So its own bracket here, we're going to bring down that 1/2. We're going to write what's inside of the square root, so 4 minus pi squared r to the 4. We're going to subtract 1 from the exponent, so 1/2 minus 1 is negative 1/2. And then we're going to multiply by the derivative of the inside. So the derivative of the inside, it's a difference rule. So the derivative of 4 is just 0. And the derivative of negative pi squared r4, we're going to take that exponent down. So it's going to become negative 4 pi squared, and then we're going to subtract 1 from there. So it's going to become r cubed. So essentially this just becomes, once we get rid of the 0, just negative 4 pi squared r cubed. So let's write that over there, cubed. And of course this entire expression is being multiplied by r. We can go ahead and close that bracket. So we're going to go ahead and make things look a little bit better here now. So v prime is equal to, and we're going to keep this part here, 4 minus pi squared r to the 4. However, let's fix up this area over here. We can rewrite this in a better form as a fraction here. So really what this is telling us is it's saying it's 1 over 2 times, and negative 1 over 2 what it's really saying is, we know an exponent of 1 over 2 is just a square root. So negative 1 over 2 is 1 over the square root of this expression. So this is going to be 1 over the square root of 4 minus pi squared r to 4 times, and we're going to bring this down here, pi squared r cubed, and then still got the r. However, let's just make this look a little bit better now. So we can see that this is all its own fraction. This you can imagine as over 1. So really we can just do 2 times the denominator times 1, and at the top we can just do 1 times 1 times this expression here. Let's go ahead and do that. I'm just going to erase what we've got here already and just make this look a little bit better instead of rewriting the line just to save some space. So what we're going to do with the negative 4 is going to be a fraction. I'm going to 4 pi squared r cubed over times r. And that is going to be our new expression. So let's continue to work on with that. So now there's 2 things that we can do here. 1, we can see that there's a 4 and a 2 here, so we can reduce. And 2, this r can be multiplied into the numerator. Once again, we can imagine this is r over 1. So denominator stays the same, r multiplies in, this becomes r to the 4. So on the line below, let's go ahead and do this. So v prime equals 1 over 3 times the square root of 4 minus pi squared r to the 4. So when we're adding a negative fraction, we can go and move that into straight negative. So while we're starting, once we reduce, we're going to end up with 2 pi squared r, and we're multiplying that in. So 4 to the 4, and then we're going to just, this 2 gets reduced. So we're just going to have this expression over here, which is the square root of 4 minus pi squared r to the 4. And that is going to be what we have now. What I'm going to do here is I'm going to take this 1 over 3 and I'm going to move it down now. So we've got v prime is equal to 4 minus pi squared r to 4 minus 2 pi squared r to 4 over the square root of 4 minus pi squared r to 4. And this is going to be all over 3. I want to go ahead and make this over 1 as well, because what I want to do is making this a common denominator will allow us to move this 3 up and just make a better looking fraction here. So let's go ahead and erase what we've got at the bottom now that we've moved it up top. So doing cross multiplication here, we can see that this and this are the same. 4 minus pi squared r to the 4. So doing that multiplication is just going to take off the square root. So v prime equals just 4 minus pi squared r to the 4. And then we're going to subtract the 2 pi squared r to the 4. And this is all going to be over that common denominator of 4 minus pi squared r to the 4. Now people can actually just go ahead right now and write that 3 up there. So now what we can do is we can see that there's like terms here. So we've got negative pi squared r to the 4 and negative 2 pi squared r to the 4. So really what we're doing is doing negative 1 subtract negative 2. So finally, our volume derivative is going to end up as 4 minus 3 pi squared r to the 4 over 3 times the square root of 4 minus pi squared r to the 4. That's clear? So that is our derivative, and now we can start to find the criticals by solving for the D and E points and solving for the zeros. Alright, so now to solve for the criticals, let's start off with solving for the zeros of the derivative. So we're going to go and solve for the numerator here. So 0 equals 4 minus 3 pi squared r 4. The calculation for this step is significantly easier than the derivative, so we're past the hard part. So we're going to move this 4 over. And 4 equals 3 pi squared r to 4. Oops, to the 4. So now we're going to go ahead and we're trying to isolate r here. We want to find the radius that maximizes the volume. So we're going to take this negative 3 pi squared and move it over to the other side. The negatives will cancel out, so we've just got 4 over 3 pi squared is equal to r to the 4. And we can write this as the fourth root. So the fourth root of 4 over 3 pi squared is going to equal r. So now we've finally got an equation for r, and going ahead with it in the calculator, again this is going to be plus and minus, we end up with 2 values. One is going to be r equals 0.606 meters. The other is going to be r equals negative 0.606 meters. However, of course, radius cannot be negative, so we're going to go ahead not use that value. So we found one of the critical points, r equals 0.606 meters. So now we're going to go ahead and solve for when the derivative is does not exist. We're going to once again set 0 equals, and now we're going to do the denominator. So 3 times the square root of 4 minus pi squared r to the 4. Dividing 0 by 3 is just going to give us 0 equals the square root of 4 minus pi squared r to the 4. Once again, squaring 0 is also going to give us the same thing. So we just got 0 equals 4 minus pi squared r to the 4. We're going to move the 4 over to the other side. Negative 4 equals negative pi squared r to the 4. This kind of looks similar to what we did before. We're going to divide. The negative also 4 over pi squared equals r to the 4. Move that over to here. We get that plus minus again, plus minus the 4th root of 4 over pi squared is going to give us the r value where it does not exist. So going ahead with that in your calculator, you should end up with r equals 0.7979 and r equals negative 0.7979. Once again, negative radius we cannot use, so we will cancel that out. So we found our two criticals, r equals 0.606 and r equals 0.7979. Now that we've gone ahead and found our critical points, let's go ahead and construct our first derivative test. So we've got the derivative, we have the original function. Let's go ahead and start constructing this table. So this is going to be, let's create a little header here. So this is going to be 0.606, which is when we found the derivative to be 0. This is going to be 0.7979, which is when we found the derivative to be dne. And we're going to plug in points over here that are less than 0.606. We're going to plug in points here that are greater than 606, but less than 0.7979. And here we're going to plug in points that are greater than 0.7979. Let's go ahead and extend that. So plugging in an arbitrary value below 0.606, I tried 0.5, get a positive number here. Between 0.606 and 0.7979 into the derivative, we get a negative number. And after 0.7979, we actually get a dne. The function does not exist. And the reason for dne is because of the height. If we take a look at it, what makes the numerator 0 is 0.7979. It's actually the same as the denominator of the volume derivative. And anything greater than 0.7979 here will make 4 minus it into a negative number. And the square root of a negative number, as we all know, is it doesn't exist. So anything greater than 0.79 creates something that does not exist. So what we see here is it's going up here. The original function, this shows it's increasing. And here it shows it's decreasing. And once again, this is dne. So what this indicates here is that we do have a maximum at 0.606. So we can therefore say that local maximum at r equals 0.606. So from here on, it becomes time to find out what is the actual volume. So we found out the radius that creates it. So now what we're going to go ahead and do is we're going to plug 0.606 into our h formula that we have from before. So plugging in 0.606 for r here and r here, we'll end up with an h value of around 0.858 meters. So now that we've found our two values, r and h, that maximize our volume, we have all we need to solve for the volume truly. So v equals 1/3 pi r squared h, and we can just sub that in there, sub this in here, and what we'll end up with, if you plug this into your calculator, is that the maximum volume is 0.33 meters cubed. So that is the maximum volume. We can go ahead and write our therefore statement, concluding statement. The maximum volume is 0.33 meters cubed. And there we go. So that is the maximum volume of an open top cone with a surface area of 2 meters squared.